My dear student, colleagues, and all the viewers watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So good evening to all here in Bangladesh and a very good afternoon to all those who are watching this program live from UK. So today we are going to welcome you all to our new session, and this session we will actually arrange a different type of webinar, and today we have invited one of the best quantum optics and atomic physics physicist from UK, and we have with us here today Dr. Professor Ifan G. Hughes, FLSW, Department of Physics, Durham University, UK, and he has already connected with us. So, sir, good afternoon and good evening to here, and thanks for accepting our invitation.
Thank you very much.
So I have already told you that we have arranged this webinar for our students to motivate and encourage them in this pandemic situation. So thanks for helping us in doing this. So before going to you, I'd like to introduce you with our student. So dear student and viewers, I think you have already come to know that the title of the today's International Physics webinar. And our today's webinar's title is very exciting. I think you will enjoy it. And the title is Quantum Optics with Atoms and Large Magnets. And our speaker is Professor Ifan G. Hughes, FLSW, Department of Physics, Durham University, UK. And we can see that Professor Hughes has completed his bachelor degree from Imperial College London, and he obtained his DPhil degree from Oxford University, and he completed his postdoc degree from two universities. One is from Yale, another is from Sussex, and then he joined Durham University in 1999. Ifan has made significant research contributions to four distinct fields of atomic physics, magnetic atom optics, spectroscopy for laser stabilization, quantitative atom-light interactions, and laser spectroscopy in large magnetic fields. His studies of spectroscopy of thermal vapors have repeatedly shown that rigorous and quantitative analysis can expose a rich set of unexpected and potentially useful phenomena and techniques. Ifan has co-authored two books that straddle his research and teaching activities. The first book is Measurements and Their Uncertainties and Optics. He has taken part in numerous outreach activities to explain his research and the mysteries of the quantum world. I think you will enjoy our this session. He's a very well-known professor in quantum optics. So thanks, sir, and
Thank you.
I'd like to welcome you again. So it's your time. You can start your session.
Great. Thank you very much. It's great that you've organised this.
Yeah,
And yes, I'm very happy to accept this invitation and talk to you this afternoon. Maybe in the future I could also come and visit you.
Oh, good. That would be very great. I will definitely invite you, sir.
Great. Yes, when the pandemic is over, it would be a fantastic thing to do. Yeah. Okay, so this afternoon I'll tell you about some of our research experiments and hopefully make a link with some of the topics you have seen in your studies and see that some of the things you see when you're taught physics is also relevant when we do physics at research level. So let me start. I'll tell you about our spectroscopy work. We use atomic vapors, so hot atoms. I'll tell you why that is and how we go about doing that. The magnet is going to play a key role. So the physics of magnetic interactions is known as the Zeeman effect. So I'll introduce that. Having shown some of the data we have and some of the experiments we've done, I'll also move on to the quantum realm. So in the quantum realm, we can think about individual particles of light, photons. And for the exciting, burgeoning field of quantum information, one of the key ingredients are single photons. They travel at the speed of light, and they're excellent mediators of quantum information. So how might one make a source of single photons using atoms and magnets is the question I will address there. And then the final topic I look at will use an experiment here on Earth, where we have atoms and lasers and magnets. But the light that we're actually going to look at is going to come from the sun. So by understanding atoms and magnets on Earth, we hope to learn about the atomic and specifically magnetic properties of the sun. And I'll tell you why designing and building these solar filters is both very interesting from a physics point of view and very, very important from a technological point of view. And then I'll draw some conclusions. So these images I have here are the glass cells, or vapor cells we call them, in which we keep our atoms. So this cell is 5 centimeters long and then is 2 centimeters wide. So this is very convenient for us to shine our laser beam through the cell. And there is a small amount of metal, and then the metal evaporates. So we call this a thermal vapor. The atoms get into equilibrium, so the atoms move around, and they occasionally collide with each other, and they occasionally collide with a wall. When we put atoms inside a magnetic field, it can be easier to make the magnetic field large and uniform over a short spatial extent. So that's the motivation for using this atomic cell. It also is 2 centimeters in diameter, but now it is only 2 millimeters across, which means it is much easier to make a uniform field. And in our research group at Durham University, the Quantum Light and Matter group, we also have an activity headed by my colleague Professor Adams, and we collaborate with a group in Armenia, and they have made some of the thinnest atomic cells in the world. So this is a picture of an Armenian cell, and the dimensions are a few centimeters tall, a few centimeters across, but the thickness can be less than 100 nanometers, which is less than the wavelength of light. So the atoms interact with light in a very different way. So I'll just quickly tell you about one experiment we do with thin cells. But again, the idea is there is a box and the atoms move around. So the dimensions of this box change, but that's basically what we're talking about. Free atoms that mostly fly through space, and then our laser beam interacts with them. So the first topic I'll address is quantum optics, and this is the team that are currently working on these experiments in the laboratory. So why are people interested in looking at atoms moving around a box? And the motivation is you can do some very, very nice fundamental physics experiments with apparatus that is quite simple. So often we have a cell and a laser. Now, sometimes there's a magnet, sometimes we have to work a bit harder on making the laser behave adequately. Specifically, it's frequency stabilization. But compared to other atomic physics experiments, these are actually rather simple. And the advantage of that is we can do modeling, and then we can have theory and experiment. And what we really like to do in Durham is plot theory and experiment on the same curve, and then see if they agree. And the nice thing about working with atomic vapors is you can have an idea, and it's rather fast to set up the experiment. So you can test your ideas very quickly. You do not have to invest many years building large, complex apparatus. So here is just a small selection of photos I've taken, figures from various research papers highlighting the kind of things you can look at. The top 3 happen to be from Durham, the ones in the dark blue. So you can make a bistable optical medium by scanning lasers through a thermal vapor. You can study these atoms in the very thin cell. All of the atoms are very, very close to the wall. And when atoms are close to the wall, they experience attraction towards the wall. So you can measure atom surface interactions directly with these hot atoms in a thermal vapor. There was a prediction a long while ago that pairs of atoms should be able to cooperatively interact, something known as the Lamb shift. And these predictions had been made, but people did not realize how to actually do the experiment. And then our spectroscopic investigations of thermal vapors gave us confidence that we understood the spectroscopy well enough that we could look for these shifts and map them out as a function of how long the cell is. So that was a demonstration of the cooperative Lamb shift, first published roughly a decade ago, and then in another atom confirming another aspect of the theory slightly more recently. And then these are figures I've obtained from these research papers from different research groups showing there's a whole host. You can look at single photons, how they walk through a medium, whether it's genuinely random or not. You can imprint shapes on laser beams, and then these laser beams can propagate through your atoms, and there's an interaction between the atom and the light, so you can change the spatial distribution. The quantity is known as orbital angular momentum, OAM. So the shape of the beam of the light, you can then shape the atoms, which in turn can reshape the light that comes out of your cell. So there's a whole host of very exciting possibilities of experiments you can do with thermal vapors, atoms in a box. So nearly all the spectroscopy I'll tell you about today is done with one atom. So we tend to use alkali metal atoms. Rubidium is our atom of choice. And the reason we choose rubidium is for the very simple reason it's a very simple element. So there is a closed shell with one outer electron. So this means we can do the spectroscopy very, very conveniently. And the atomic physics of the alkali metal atoms is the simplest possible spectroscopy to do. So as it happens, rubidium has two isotopes. Roughly 3/4 of the atoms in the box are rubidium-85 and roughly 1/4 are rubidium-87. And then the notation people use is, so the first, this is the ground state in rubidium, and then the first excited state is known as 5p, and there's a splitting. There is a 5p 3/2 fine structure, and there is 5p 1/2 fine structure. And if you go from the ground state to 5p 3/2, for historical reasons, that transition is known as D2 and is at 780 nanometers. So your eye can only just see this color. It's a very, very dull red. You can also go from the ground state in rubidium to the lowest fine structure state in the first excited state, 5p 1/2. And then historically, this is known as the D1 transition. And this is also in the near infrared, 795 nanometers. So the good news is these infrared resonances coincide with light emitted by diode lasers. And diode lasers are used in things like DVD players, CD players, etc. So the spectroscopy of rubidium is particularly useful for two reasons. Rubidium itself is a simple element, and the availability. So there are convenient and cheap diode lasers with which you can do the spectroscopy, study how the light propagates through the medium. So many years ago now, we started on an activity to try and explain what happens when you shine light at atoms in a box. So the key concept is the atom is neutral, but the electron is much lighter than the nucleus. So when the electric field of the laser hits the atom, the electron gets accelerated, and the accelerating electron radiates waves. So then there are two electric fields in the cell. There's the electric field from the laser, and there's the electric field from the atoms. And then you add these two electric fields. And sometimes they can get bigger, sometimes they can make themselves smaller. So destructive interference. So the key question is, if I shake an atom, how large is the response? And this quantity is known as the electric susceptibility. So it's the electric field of the laser that's doing the shaking, and the susceptibility tells me the strength of the atom-light interaction. So we have shortened and concatenated that into Alexis. So Alexis is our code, and it's open source. So you can download it from here and run it. and there's the slightly more modified and up-to-date version here. So what does it do? So we think of the atom as having energy levels. So there is gross structure, then there is fine structure, then there's hyperfine structure, and finally the Zeeman effect. So we write down a matrix for each of these terms, and then we calculate the atom-light interaction using this Hamiltonian matrix. Sometimes we can diagonalize the matrix and get analytic results, but more typically we use computational techniques to find the eigenvectors and the eigenvalues. So the eigenvalues tell you the energies of the atom, and the eigenvectors tell you about the shape of the distribution of the electron in the atom. And that tells you how strongly the atom interacts with the light when you try and shake it. And then, having found the energy levels, there's the question of how wide are the energy levels. And the atoms in our box move. So some of the atoms run towards the laser, so they see a higher frequency. Some of the atoms run away from the laser, they see a lower frequency. So this is the Doppler effect. So there is a well-known formula for the Doppler effect, which gives us a Gaussian distribution of velocities of the atom map into a Gaussian distribution of frequencies. But if the atoms were stationary, the excited state has a finite lifetime, and because it has a finite lifetime, we can use Fourier properties to predict that the atom will decay exponentially in time. And the particular form it has is exponential decay. So the exponential in time is associated with a Lorentzian profile in frequency. And if you convolve the Lorentzian from the natural broadening with a Doppler broadening Gaussian, because the atoms move, you end up with what's known as a Voigt profile. So it's a slightly cumbersome formula to write down, but modern computers can evaluate it very, very efficiently. So our Alexis code you can download, as I said earlier, for free, run it, and it has a GUI, a graphical user interface. So you can type in which atom you're interested in, whether you're doing D1 or D2, which magnetic field you have, the temperature, the cell length, etc., etc. And then it makes a prediction. So for rubidium, there were 2 split ground states, so I would expect to get 2 lines. But as I said earlier, there are also 2 isotopes. So in fact, you would predict 4 lines, and that's exactly what we see here. So this graphical user interface is very useful for understanding how the light propagates through our cell. And that allows us to make predictions of which parameters we should choose in the laboratory before we do our experiment. So that's very, very important. We can leave our computer running, optimizing a particular question. And then overnight, the computer tells us, right, we should choose this temperature for this length of cell for this magnetic field. And then what we find is we go to the laboratory and we choose those values of the parameters. And then we get excellent agreement between the theory and the experiment, as I'll show you in a few slides' time. So behind the scenes, as it were, this is what Alexis actually does. So I've got an atom here with a transition. I've chosen a magnetic field. You would expect to get 8 transitions. These 4 for one circular polarization of light, and these 4 for the other circular polarization of light. So what the Hamiltonian tells you is the locations of these energy levels, and it also tells you the relative heights. As it happens, all 4 here are similar, and these 4 are similar. And then we add this line shape. And the electric susceptibility, this chi, is complex. So it's a complex number. So it has a real part and an imaginary part. What does that mean? So one thing we know about atoms interacting with light is, for example, if I send laser beam through glass is a polarizable dielectric. We're familiar with 2 different phenomena. At the other side of the glass, there is less light. So some of the light is absorbed, some of it disappears. There's loss. And that is proportional to the imaginary part of the susceptibility. So the absorption of the light, the fact that it gets extinguished, there is less light at the end. You learn about that from the imaginary part of the susceptibility. But the other phenomenon we're familiar with is the speed of light slows down. So the time it takes light to propagate through a certain thickness of glass is longer than if you had vacuum. And this is the quantity, the refractive index. It tells you how much slower light moves in the medium. So this is typically called N for refractive index. And N is directly proportional to chi r, the real part of the refractive index. So this is a very nice feature of Alexis. Alexis calculates the complex susceptibility, and that allows you to calculate how much light comes through the cell and how fast the light comes through the cell at every color. And then we can add up all of the electric fields, and that tells us how much light comes out. So one of the simplest experiments you can do if you're doing atomic spectroscopy is this one. You get your cell, it might be 5 centimeters long, it has some rubidium, it's at roughly room temperature, and the atoms move around. And then you shine your laser beam through your cell, and you have one detector, and you measure how much light comes through. So this is the D2 line. So we expect that you can go from this quantum number f to the excited state, or you can go from this quantum number, which is 1 lower, to the excited state. And that gives you two distinct frequencies that are separated by the hyperfine interval. This is hyperfine splitting in the atomic ground state. Now for rubidium-85, that hyperfine interval is approximately 3 gigahertz. This is the laser frequency in gigahertz. For rubidium-87, the splitting is more like 6 or 7 gigahertz. If you use cesium, the answer is 9 gigahertz, which is the fundamental definition of the atomic clock. So what we expect is 4 lines. Rubidium-85 will absorb at 2 colors, and rubidium-87 will absorb at 2 colors, and that's what you see. And then if you increase the temperature of the cell by 10 degrees, the metal, which is at the bottom of the cell, evaporates. And the very good news is there is a rough rule of thumb. If you heat the cell by about 10 degrees, you get twice as many atoms. So in going from one temperature to 10 degrees hotter, you see there is much more absorption. And if you heat the cell by another 10 degrees, there is another factor of 2. So we get even more absorption. So this is one of the very nice features of doing spectroscopy with alkali metals. If you want more signal, you can gain factors of 2 really, really easily by just heating the atoms in your box. And then depending on how good your resolution is, you might think there are 3 traces here, but if you look really carefully, there are 6. So the black dashed line is theory from Alexis, and we also have the smooth red curve, continuous, which is experiment, and clearly they lie on top of each other. So that gives us great confidence that our Alexis code successfully accounts for the atom-light interactions in this Doppler-Brogden spectroscopy. So because the agreement is so good, what we actually do is plot the difference between these two. We call the difference, the residuals, and we have to multiply by 100 just in order to make the difference visible. So we're very happy that our residuals are on average about 0.1% RMS. So the agreement between theory and experiment is good to about a part in 1,000 typically. So if you want to read about the theory and how we did the experiment, you can find that in this paper. And there's a question of how weak you need to make your laser beam so that the presence of the light doesn't perturb the atoms. And that paper in the American Journal of Physics will tell you about that. Okay, let's move on to the atomic magnetism side. So if you have a weak magnetic field, the atom has a magnetic moment. So the angular momentum F is proportional to the magnetic moment. And F is the sum of 2 things. The electron, I'm using the symbol J for the spin of the electron, and I is the spin of the nucleus. And I and J add up to make F, and then F precesses around the magnetic field. So that's typically what you have with weak magnetic fields. The regime I want to go into is known as the Paschen-Back regime. So what's the idea there? The idea is these 2 magnets couple strongly, and then they slowly process about this magnetic field. So I want to change that. I want to make the magnetic field very, very strong. and then the magnet associated with the angular momentum J precesses around B, and the magnetic moment associated with the angular momentum I independently precesses around B. So I've broken the F quantum number, so neither the F quantum number nor the MF quantum number are very good anymore, but the projection of the I and J, the nuclear and electronic spin, onto this axis are labelled MI and MJ. They're good quantum numbers. So when I get into this field, what actually happens is the atomic structure gets simple, which is the motivation for doing it. So how do I do that? I go back to my Hamiltonian. I have my bare energy, my fine structure, hyperfine structure, and now I add in the very well-known atomic interaction for an alkali metal atom. So in rubidium, all the transitions and transition strengths are known phenomenally well, which is good, because then we can put that into our matrix and then get the computer to diagonalize the resulting matrix, and it tells us how to calculate the energy levels, where they're situated, and how strong the transitions are. So here I'm plotting an energy level diagram. So this is energy on the vertical axis and as a function of magnetic field. So if I have zero magnetic field, I see what I showed earlier. This is the 5s½ ground state. This is the 5p 3/2 excited state. And if I add a modest magnetic field, these energy levels split. That's the Zeeman effect. And when F is a good quantum number, so when F is 2, I have 5 projections. MF can be +2, +1, 0, -1, or -2. And I also have F is 1. So I have 3 projections. F can be -1, 0, or +1. So that's a nice simple diagram. However, if I increase the strength of the magnetic field, these energy levels become non-linear. So I've hidden all the details behind this panel. But the regime I'm interested in involves going down the axis to a magnetic field of the order of 1 Tesla, which is a very strong magnetic field. And what happens there is you see these energy levels become straight again. So when the energy levels are straight, that means the atomic states have got a very well defined magnetic moment, MJ, and this means that MJ and MI are good quantum numbers. So down at this end of the diagram, I have nice new symmetric quantum numbers, which is much easier to deal with than what happens for a moderate field, where the energy levels show a non-linear dependence on magnetic field. So I can now use Lexis to make a prediction. So now I'm plotting on this axis the frequency, and on this axis I've cascaded different spectra for 0 field, 500 Gauss, 1 kilogauss, etc. And what you find is for 0 field, you get these 4 resonances that I saw before. And then as I increase the magnetic field, I've also sketched here the transitions. So the red ones are associated with one hand of light, and the blue ones are associated with another hand of light. And the red and the blue partially overlap. So it gets really, really complicated. So these are very, very peculiar line shapes. And if you go up to 1 kilogauss, it's still quite a peculiar line shape. But as we go further down this diagram, you see a very nice evolution. We now have 4 states up here and 4 states down there. So the spectrum has evolved from being degenerate to very complicated back to very, very simple. And crucially, for very large magnetic fields, what you see is that the Doppler width, which tells you how wide these individual resonances are, is less than the separation. So back here, there are in fact 8 transitions, but they all overlap, so it's rather complicated. Down here, there are still 8 transitions, but now they're very well resolved, and that's our motivation for using the hyperfine Paschen-Bach regime. So let's show you what happens when we do this in the lab. So it's a rather simple experiment. It's a similar cell to the one I showed you earlier. We actually use a very large magnetic field, 1.5 Tesla. We heat the cell by about 100 degrees in order to get enough atoms. It's a short cell in order to fit inside the magnet. And then what we see is this. So this is the textbook diagram of how the atomic energy levels spread as a function of magnetic field up to 1.5 Tesla. And then at 1.5 Tesla, I get these nice isolated resonances for the ground state and the excited state. And then you can see that these transitions are associated with, there are 8 of them associated with right-hand circularly polarized light. These 8 transitions are associated with left-hand circularly polarized light. And these 8 transitions are associated with what are known as pi transitions, where my magnetic field and the electric field of the laser are parallel. So now I get 24 transitions. And the good news is they're distinct. So it's 4 here, then another 4, then another 4, and then the whole thing is symmetric. And if I had a much smaller magnetic field, most of those 24 lines would overlap, and it would be very, very complicated to try and do any analysis. So that's the energy levels. We then used Alexis to predict some features. So the top one is the transmission, how much light comes through. So this is also known as S0. So Stokes is the physicist whose name is used in understanding how polarized light goes through magnetic fields with atoms. So S0 is how much light comes through. And what we see there is exactly what I showed you in the last slide, 24 resonances, each of which is absorbed, and each of which is very well resolved. So the Doppler shift is less than the Zeeman shift. And then S1 and S2 tell you that as the light goes through, the plane of polarization might rotate, and that the plane of polarization rotates very strongly close to an atomic resonance, which makes sense. S2 tells you about a rotation about another axis. And then S3 is this really crazy line shape. So what does this tell us? S3 tells us how different the right-hand circularly polarized light is to the left-hand circularly polarized light. So if the atom absorbs one of the hand of light, the light that comes through the medium will be the other hand, and then we'll get very large values positive for S3. If we flip the magnetic field such that the first hand is now transmitted and the second one is absorbed, S3 will be large and negative. And this very, very peculiar line shape is what our computer code tells us should happen. So it's very difficult to try and predict in advance what this line shape looks like, but our computer diagonalization tells us that's the answer. So having made these predictions, we then went to the laboratory and tried to measure these things. So there's the data. Francisco's thesis came online earlier this month, and you can read about his thesis work in this paper that was published earlier this year. So what we have is, again, purple, smooth and continuous is our theoretical prediction from Alexis, and the blue distinct dots are our experimental measurements. And in this first configuration, we've chosen the electric field to be parallel to the magnetic field, so you'd expect strong pi transitions, they're called, close to resonance, and that's what we see. And then the sigma plus and minus transitions are much weaker. And again, theory and experiment are phenomenally similar, which is why R, the residuals, is the difference between them. Again, we've had to multiply by 100 in order to make that visible. And then to check the theory, we rotated the plane of the light before it went into the cell, and in that geometry you would expect to get far weaker pi transitions, which is what we see, and far stronger sigma plus and sigma minus transitions, which is what we see. So again, there are 24 isolated atoms here, and the residuals are again very small, and we have to multiply by 100. So you can think of this as we're essentially doing 24 separate experiments, and each experiment looks like this: 1 level, 2 level, light. So in many, many textbooks about quantum mechanics, they tell you about the 2-level atom. And what we've done is realized the 2-level atom, but actually we've got 24 copies of it showing slightly different versions. Was if we didn't have a magnetic field, most of those energy levels would coalesce, the spectra would overlap, and you wouldn't get this very, very simple 2-level picture, and the theory would be very, very difficult. And then we also looked at the rotation of the plane of polarization of light coming through our strong magnet. And here's our prediction for S1. And again, theory and experiment show excellent agreement. You get a large amount of rotation in the presence of an atomic resonance. And here's that theoretical prediction in dark blue of the S3 parameter. How chiral is the light? Is the light rotating this way, or is the light rotating that way? So at the peak of this curve, the light is chiral with one sense, and at the trough, the light is chiral with another sense. And then we see this fantastic result that despite this line shape being absolutely crazy, I mean, who would have guessed that the answer was going to be that? You see our experimental points, the dark purple, lie on top of the blue continuous line. And again, we have to multiply the difference by 100 to make it visible. So despite this being a really complicated interaction, our code agrees with nature, what we see in the lab, which gives us great confidence that we've understood how the atoms, lasers, and large magnets are all interacting. So let's move into the quantum realm. So we're now going to do an experiment with the same atoms, rubidium, but with 2 laser beams, and the atoms are in a magnetic field. So here's the idea. I can promote the atom from the ground state to the first excited state with the same laser that I showed you earlier. But I can use a slightly different laser to go to the second excited state. So this is a 5s, this is 5p, and this is 5d in rubidium. So 2 lasers can doubly excite my atom, promote the population to 5d, and then I wait. And there is a process known as spontaneous 4-wave mixing. So what are the 4 waves? The 4 waves are these. Wave 1 is one of my laser beams. Wave 2 is my second laser beam. And then the atom generates waves 3 and 4. So it falls back to this excited state, emitting what we call the signal. And it also can fall back from that excited state back to the ground state, emitting what we call a herald. So this is in fact the D2 transition, and this is the D1. So you get a pair of photons being emitted simultaneously. Now, why is that interesting? That's interesting because of the names I've given them, gives you the clue as to what we're about to do. Because you know there's a pair of photons, if you detect this photon, herald, which gets emitted in a certain direction, you know that there has to be a photon in the signal beam, which is going in a separate direction. So in quantum computing, quantum information processing, to transfer information between quantum computers, light is by far the best mediator of quantum information because it moves at the speed of light, and you can encode quantum information into the polarization states. But what's very difficult to achieve is a source of single photons. You have to make one photon carry the quantum information for 1 qubit. So this now starts to look like a source for these single photons, because if I detect a herald, I must get a signal. So that's the idea. So what does the experiment look like? Hopefully similar to what we've seen previously in the last half an hour. I now have 2 laser beams. Here's my strong magnetic field, and there's my thermal vapor. And now I must arrange these 4 waves to be in certain direction. So we know about 2 fundamental things that are true when we look at atom-light interactions. So the first one is energy is conserved. So the sum of the energy of this photon and that photon is exactly the same as the sum of the energy of the 2 emitted photons. So that tells me which energy levels I can use. But this 4-wave mixing process, which emits beams of light, also happens when momentum is conserved. So the momentum of the photon is proportional to its k vector, 2 pi divided by its wavelength in magnitude, and the direction is the direction of the beam. So if I arrange for the 4 laser beams here, well, the 2 beams and the 2 light sources I'm generating, if their k vectors form this closed shape, then that's known as phase matching. And the waves moving through the atomic medium are in phase with the waves being radiated, and they all add up constructively. So if I maintain the phase matching geometry and conserve energy, then my prediction is in this direction, straight through, I should get this herald photon. And at that angle, I should get this signal photon. So then we use different filters to throw away all the other light. And now I'm doing this with very, very weak laser beams. So rather than have a macroscopic amount of light, I have a device known as a photon counter. And photon counters gives you a click when a single photon hits them. So after a single photon is emitted, I look for clicks on my photon counters. So if you're doing that, you're genuinely doing quantum optics. So what you see, so the excited state decays with a exponential decay, as I told you earlier, of about 20 nanoseconds. So the naive expectation is when you count 0 is when you find the herald that you look for signal, you would get an exponential decay. But what we see are these oscillations. So it's definitely not a single exponential decay. There seems to be a beat. So where does the beat come from? Beats come in physics when you have two waves and the difference between them is much smaller than their independent frequencies. So what's actually going on is if we look at the atom-light interaction, there are two classes of atom speeds, one close to 0 and one that's finite. So the presence of the laser beam splits the energy in the atom into two pairs of energy levels known as dressed states. The dressed states have got slightly different energy, and that means that different atomic speeds are resonant with them. And then they emit with 0 Doppler shift for these atoms and a finite Doppler shift there. So because there are two slightly different frequencies, we see this beat. And when we change the location of the laser in this diagram, we basically map out the gap between these two dressed states. So there's a small gap, there's a larger gap, and as the gap gets even higher, the oscillation gets even faster. So this was the first time someone had seen such a nice, simple result with a thermal vapor, and we were only able to see it because we'd used the large magnet to achieve the hyperfine passion back to achieve a very simple atomic energy level diagram. If you try to do this with atomic rubidium, not in a large field, this picture would be very, very messy. There would be energy levels everywhere. So that's a slightly different picture of what happens. So we put in two laser beams. We happen to call them the pump and the coupling beam. And then there's an interaction. Two velocity classes of atoms can emit. If we measure this herald, then the signal can have two colors. So this is what's known as a collective emission. So usually we think of light as being emitted by one atom. And if there are many atoms, you get more light. But actually what goes on here is very, very different. We only have one photon, but the photon isn't being emitted by one atom. If you write down the quantum mechanical wave function, what you find is this thing. It's known as a collective state. You can make an entangled atomic state, which is an interesting resource for quantum information. And the idea is that the two waves we put into the medium, they write phase into every atom. So we call this a collective state because basically all of the atoms have that information in them and all of the atoms radiate and you get interference, and it's only in these phased matched directions that you actually see your single photon. So this is a very, very curious quantum phenomenon that we measure one photon, but we don't actually know. We can't know which atom emitted it because it's emitted by all of the atoms. Okay, so there's a test you can do if you think you have single photons. So this is the apparatus again, and now I've added on to the end. So in quantum optics, there's something known as the Hanbury-Brown-Twiss interferometer. So let me tell you very quickly about that. It's a very simple concept. You have three detectors. So you send your herald onto detector 0. When that goes click, you look at what happens on detector 1 and detector 2. And if you have a strong laser beam coming in this direction, half of it would go down from this polarization beam splitting cube, and half of it would go through. So then you would get numerous clicks on 1 and 2. But if you genuinely only have one photon in the signal beam, you can't split a single photon. So either it gets reflected, as I've drawn it there, so 2 would give a click at the same time as 0, or the single photon goes through, and 0 and 1 would give you clicks. So the prediction is we're looking for large numbers of clicks of 0s and 1s. We're looking for large numbers of clicks of 0s and 2s, but we should find a huge suppression of simultaneous 0, 1, and 2. So the triple coincidence rate, that's called, should be greatly suppressed if we've actually made something that approximates to a source of single photons. So that's the apparatus again. We're making this light, and this is my 3 detector Hanbury Brown Twiss interferometer. And here's the output. So I'm plotting here the correlation. So I ask, if I see a herald photon, how likely is it that I see a signal photon? And 1 is the normalization of this quantity, such that if I have a conventional laser beam, the answer is 1. And what you see in orange is a huge enhancement. So GHS means if I see a herald photon, I'm overwhelmingly more likely to see a signal photon, which is good. Green is GHS2. So this means if the herald photon detector clicks, I'm also very likely to see another click in the second signal beam. And the good news is what is very suppressed compared to the orange and green is this blue. And blue is the triple coincidence. What's the probability of, if I detect a herald photon, simultaneously detecting signal photons at detectors 1 and 2? And it isn't back to the background level, which is what we would have liked, but it is clearly greatly suppressed. So the figure of merit in this field is known as this G2. For normal laser light, the G2 definition tells you that you get 1 for the correlations everywhere. And if you get a dip, so if G2 is less than 1, time 0 means I'm looking at events that happen at the same time at the detectors. Tau is the difference in time that the photons get collected. So I would like to get a dip in G2, and that is a mark of the purity of my single photon source. And what you see is 1 in the wings with some experimental noise, and clearly a huge dip, which gives us some confidence that our hot atomic vapor in a large magnetic field does have some relevant properties for single photon generation. So this data is very new. It hasn't been published in the research literature yet, but if you're interested in more details, that's the PhD of my student that you can obtain online. And then the very last topic I want to tell you about is we can do the same thing with extremely short cells. And this is just to confirm that. So when I make my cells 30 nanometers thick, it's 6 orders of magnitude shorter than the first cell I showed you, we can still obtain very, very nice rubidium spectra. They do get broader because the atoms are hotter, but we can work in these nanometric scale vapors. So there's a lot of activity at Durham University about that. It's headed by my colleague, Professor Adams, and that's the current nanocells team. We collaborate with a group in Germany, and another group in Armenia made us the cell. And then I want to finish by telling you about this very exciting recent development. So far I've told you about experiments done on Earth with atoms, lasers, and magnets. But what we want to do now is learn about the magnetic field on the sun from atoms emitting light that we then collect on Earth. So why might you want to do that? So the concept is the sun is an active object and it has magnetic storms, and it kicks off and radiates a whole host of light, particles, and other things which can propagate to Earth. So there's a complicated interaction between objects emitted by the sun and the Earth's atmosphere. So space weather is the concept. And it has potentially a large impact. So clearly we're all familiar with the positive impact the sunlight has on our lives, but some of the magnetic phenomena are potentially much more devastating. So you can have magnetic storms which then propagate to Earth. And at the end of last century, there was a disastrous consequence when in Canada, a power network was taken down by one of these magnetic storms, and a large modern city had to work without electricity for a fraction of a day, which had devastating consequences. So there are monitoring stations in the UK and the US and Canada, all over the world, looking at the sun and trying to predict when these coronal mass ejections, they're called, might happen. So they are solar flares, and they can be used to predict when these phenomena could propagate through to Earth. So using various techniques currently with large computers, you can maybe have a 6 up to 10 hours forecast telling you something could happen in the near future. What would be far more useful would be to understand the magnetic properties on the sun and then be able to predict solar weather up to 2 or 3 days in advance. So if solar forecasting got to that high fidelity predictions with a day lead, that would be revolutionary. So how are we going to do that? So we at Durham are part of an international network known as SAMnet. So it's an international network, and the idea is to have these devices based on telescopes at various locations in the Earth, one at every time zone, continuously monitor the sun. And the question is, what you learn from taking pictures of the sun on Earth about the magnetic field. So the sun is a very complicated object, but the good news for us is the surface of the sun, the photosphere, is at about 6,000 Kelvin. And then in the next few megameters above the photosphere, there are some atoms. And these atoms absorb and emit light. And we can use our understanding of the interactions of atoms and magnetic fields on Earth to understand what happens to the magnetic fields and the light being emitted on the sun. So the light that's emitted on the sun and we measure on the Earth tells you about the magnetic field from different atoms. And then there's some rather complicated mathematics that allows you to convert these magnetic field measurements into predictions of solar weather. So we are interested in very simple atoms: potassium, sodium, calcium, helium. And the reason you're interested in more than one atom is the different atoms live at different heights above the photosphere. So close to the photosphere, the lower chromosphere, up to about a megameter in the upper chromosphere, and then eventually into this transition region. So the idea is, if we look at different atoms on the sun, we can measure magnetic fields at different heights, and that's the information that the mathematical modeling needs to tell us about the magnetic field behavior. So if you look at the sun, there are these objects known as sunspots, and the idea is we're going to be able to quantify the magnitude of the magnetic field in these active solar regions by using atomic filters here on Earth. So you can read about our paper, which has just become available, on how we're intending to do that in this journal. So the very last thing I'm going to tell you about is the link between the first half of my talk and the last half. How does this work? It's very simple. Again, we think of linearly polarized light as being made of left and right circularly polarized light. They propagate with different speeds through a medium where there's a magnetic field. So if you have two polarizers, you can play with the angle between them and go from light to grey to black. But if between the polarizers you have 3 sheets of sellotape of different thickness, what you find is this incredibly colourful pattern. So why are there different colours? It's because the sellotape is birefringent. So the refractive index for left-hand circularly polarized light is different to the refractive index to right-hand circularly polarized light. The light rotates and you get different colours. So that's a magnetic optic phenomenon first discovered by Michael Faraday, so it's known as the Faraday Effect. So what we're going to do is have linearly polarized light passing through our hot vapors. We have a large magnetic field, and then at some colors, the light is rotated and comes through our filter, whereas at nearly every other color, the light does not get rotated, and this polarizer eats the light and no light comes through. So we can use atoms, and this is our work at Durham, to make the narrowest possible atomic filters. There's some curves showing you the refractive index and the absorption, which is similar to the Stokes parameters I showed you earlier. And this is a nice paper explaining how this Faraday filter works. But the idea is to make these very, very narrow atomic resonances and use them to learn about the magnetic field on the sun. So there's the summary of that. There's the sun with active solar regions. These are the atoms we're going to look at, alkali metals, calcium and helium. This is a photograph of the apparatus we have now built at Durham with optical elements. This is the large magnetic field in which case our atoms on the Earth live. And these are our theoretical predictions of the different Stokes parameters on how to achieve filtering. And this is a picture of the magnetic field we achieve inside our very large magnet here on Earth, which allows us to learn about the magnetic field on the sun. So that's the team that I collaborate with on the solar filter project. So to summarize, I've shown you that atoms, lasers and magnets go very well together. We can make very nice 2-level, 3-level atoms that you learn about in your quantum mechanics textbooks. We've actually modeled this in our lab, done the experiment, and we get excellent agreement between theory and experiment. I showed you a quantum optics experiment where you can use single photons, entanglement, and then we looked at heralded single photon pairs. And lastly, I told you how our understanding of atoms, lasers, and magnets interacting here on Earth is going to be used to take light that's been emitted by atoms on the sun and measure the local magnetic field on the sun at different heights in order to help predict space weather such that we can get more warning before there's any coronal mass ejections coming towards us on Earth. And I'd just like to thank the people who've worked with me historically and the people who give me funding. Great. Thank you very much for your attention.
Thank you, sir, for your wonderful and exciting lecture, sir.
Thank you.
So we have got few questions. So if you allow, we can start our discussion.
Oh, yes, please do. Yes, please ask questions.
Okay, the first question: what is the Herald signal photon?
So the atom in our experiment emits 2 photons, and you can choose to call one of them herald and the other one signal. It's arbitrary which one you call which, but because they both get emitted simultaneously, the idea is you know that one photon is coming in this direction if you've measured in the other direction. So the concept of heralding is it tells you when to look in the other direction, because of course we have a detector that looks at single photons, but our hot vapor cell, it emits billions of photons, so you can't look at every photon that comes towards your detector. There's just an overwhelmingly large number. So if you didn't have a herald, it would be hopeless to try and look for the one photon we're interested in, because it would be immersed in a huge sea of other photons. So the advantage of looking at this correlated pair is if you detect one and you call that herald, the other one has to be in the very, very specific direction in which you're looking.
Okay. Thank you, sir. We have another question. So in comment section, you can see also. So can we probe Planck scale physics with quantum optics?
So a few years ago, I think I would have said absolutely no. But recently, in atomic physics, in the realm of quantum optics and atomic physics, some of the most startling breakthroughs have been in making an atomic clock. So I showed you a 2-level atom and told you how that interacts with light. So if you count how many times the atom oscillates when you shake it, that essentially gives you a clock. And the most precise atomic clocks now have improved by up to 6 orders of magnitude in the last decade. It's startling, the progress on atomic clocks. Now, what that means is atomic clocks are very sensitive to any small change. And if you have one atomic clock and a second atomic clock, and you locate them in different directions, in different locations, you can measure things like gravitational fields. And then the question is, what fundamentally is the origin of the gravitational field? What is the length scale of variations of the gravitational field? Space-time itself, if that's quantized, is there a fundamental Planck length? And now I would say that there are realistic prospects of using modern contemporary atom laser phenomena to learn something about Planck scale physics. So it hasn't quite happened yet, but I can imagine it will happen. Whereas, as I said, approximately a decade ago, I would have answered that question with a categorical no. But very excitingly, the progress in atomic physics and quantum optics is so rapid that I can foresee that there will be experiments that probe these kind of length scales soon.
Okay, sir, thank you. We have another question. So, can you use a quantum sensor for the absolute neutrino mass measurement?
So let me think about that. I think the difficulty with measuring neutrinos is the weak interactions of neutrinos on matter. So typically you have to have a very, very large detector. And in the experiments I've been telling you about, essentially we're going in the opposite direction. So we're using single atoms. So if you want to try and measure the interaction of neutrinos with single atoms, I believe that for that the cross-section is prohibitively low, and that your signal rate would be so abysmally low that you couldn't really do it. You have to use a macroscopic amount of matter to look for neutrinos and their interaction with matter, and that isn't really a quantum sensor, no.
Okay, sir, thank you. Yeah, we have another question. So, is it simulation results or experimental? If simulation, then which software is used?
Both. Yep. So this afternoon I've showed you simulation and experiment, and the simulation is done in Python. So the language we choose to use is Python. And if you look back at the webcast, I've actually given the web pages for the references for the paper. So if you want to run Alexis, it's written in Python. Python is our language of choice for doing all of the simulation. Yeah.
Okay, thank you, sir. We have another question. So, are there challenges in optics?
What an excellent question. Very good question. Yes. Of course, when I present an hour of my work, I present all the highlights. I don't tell you what the challenges are. So there are experimental challenges, and that's associated with the question I showed right at the end. So our heralded single photon source, it's very difficult when we're looking at very few photons, because in our laboratory there are other things that also emit photons. So what's very difficult to achieve is to find the photons you're interested in. Now, there are clever techniques like this heralding tells you when to look. We can use atomic filters to throw away most of the photons that are irrelevant. But fundamentally, what you're fighting against is when you're doing a genuine quantum experiment, when I'm talking about one photon being emitted from one atom, clearly you're very prone to noise. If there's anything else in your laboratory that emits more than one photon that your detector detects, the risk is the one photon you're interested in disappears into some sea of other photons. So the biggest challenge in quantum optics is to try and isolate your system and to try and reduce the noise levels such that the photons of interest to you, maybe they're mediating some quantum information. You want the person who you're sending the quantum information to get your photon, but not other photons. So there are techniques. It is possible to, well, people have started doing experiments, but that still is one of the biggest challenges, is how to eliminate every other source of photon that could also get into your detector. Yeah, what an excellent question.
Thank you, sir. We have another question, sir, from the same person. So, are there unsolved problems in quantum optics?
Yes. Oh well, I could give you a whole week of unsolved. Yes. So again, clearly, I've highlighted the things that we understand and that we work, but there are simple questions that people don't fully understand the answers to. So even when I told you about the collective Lamb shift, the picture there is there are two atoms and that they share a photon between them. So there is some theoretical understanding of how that works, but the theoretical understanding is not complete. Then there are complexities, like we have to place our atoms within a box. So the atoms are close to surfaces of walls. So how should you take that into account? How does the motion of the atoms? So despite the system being pretty simple, it's amazing how nature reintroduces more and more layers of complexity. And each layer of complexity you add means you have to think deeper and work harder in the laboratory to try and conquer them. So there are plenty of open questions, and they typically are associated with going up from 1 to 2 to many. That's basically the hierarchy. Yeah, excellent question.
Okay, sir. And this may be the last question. So, is there a non-destructive detector for propagating single microwave?
So there is a whole field of quantum optics known as QND, quantum non-demolition measurements. So the short answer is yes, in theory, but actually realizing it in practice might be difficult. So again, many years ago, the people who founded quantum mechanics thought that if you detected a photon, you would project and then you would lose some information. But since then, so if you were to look for further information, the topic you should be looking at is quantum non-demolition measurements. And there are, in theory, protocols for doing this. Quite how efficient they are with microwaves, I'm not an expert in that field, but I know that theoretically it has been conceived of a route of doing this. Quite what the current laboratory state of the art is, I'm not confident of answering that part of the question, but what I know is that in theory one can do that. Yes, that's right.
Okay, sir. Thank you for your wonderful presentation and discussion session. I think it is a very good opportunity for a student and the viewers to learn a lot of things about quantum optics, and they have actually it's a great opportunity for them to interact with you directly, and they can ask question, and they have already asked some interesting question. So thanks again for giving us this opportunity, sir. And as you have already mentioned that in near future we can arrange a face-to-face session after the COVID pandemic, and
that would be
wonderful.
Yes, exactly. That would be splendid. I very much enjoyed interacting with you through the computer this afternoon, but were we to be able to do this face-to-face in the future, that would be absolutely splendid. Thank you very much.
Yeah, it's my pleasure, sir.
Bye.
So, bye, sir. Have a nice day, sir.
Yeah.
Good night.